I'm not sure about 9 and 10. I thought I saw a pattern, but I don't know if I.
Yeah, you're correct with yeah 9, and then yeah 10 would be AB AB. We can just kind of go ahead and work through that one quickly. Like you just plug in A10 would be A10 divided by 2 B, so A5B, and A5 was ABA, so this would be AB AB. Good. So are there any questions on how we found um, any of the elements of the sequence? Yeah, Stephen.
And this is just a sort of brute force calculation, is my guess.
We just brute forced through all the elements. We just basically here we're just plugging into the recursive formula and just trying to see if we can find the first 10 elements. Just brute forcing it.
Yeah, thank you.
Any other questions? Awesome. So let's go ahead to part B. So part B is a lot similar. So here we're just determining what A17 and A21 are. So basically same kind of brute force technique, and we can just kind of go through that together. So to find A17, right, 17 is odd, so we use the second formula. So we'll do A17 minus 1 divided by 2A. So that'll be A16 divided by 2, so A8. And then if we recall on the previous slide, we figured out that A8 was ABBB. So this will be ABBB A. And then similarly for A21, 21 is odd, so we use the second part of the recursive formula. So A21 minus 1 divided by 2A. So that'll be 20 divided by 2, which is 10, so A10A. And then A10, if you recall, was ABAB. So this will be ABABA. So any questions here?
James, there are a couple of questions in the chat.
Oh, perfect. So yeah, first one is brute force the only way to solve a recursive formula right? For this problem, yes, and that's because it'd be difficult to like come up with a closed form for this because we're kind of concatenating elements onto previous elements. So it'd be extremely difficult for us to find a closed form in this case to just figure out whatever the nth element is. So for this one, yes, but in general, sometimes, and for a lot of the problems we deal with, if we have a recursive form, we can often figure out what a closed form is as well. And then somebody else asked, it might be possible to create a closed formula based on the recursive, but otherwise it seems like you're right. Yes. Yeah, so it might be possible to come up with a closed form here, but it would be pretty difficult to figure out one. So yeah. Any other questions? Okay, so in chat, it seems like you might be able to solve it by converting the index to a binary with A representing 1 and B representing 0. Could we use some closed form to convert it? Yeah, you probably could use binary to do this, and it would probably involve some calculations with binary to figure out what the nth term is. So you'd kind of convert these to binary, convert each of these to a binary number. And then you could possibly figure out a closed form based on that. That's a little bit outside the scope of what we'll be doing with this in this class. But yeah, really good question there. All right, so if that's all the questions on this, we can go ahead and move to part C. Again, very similar to the previous parts, but this one is just assuming if we know that A315 is this sequence, can we figure out the value for A630 and A631? And we just use, again, same technique we used on the previous pages. So we can just go through that together. So for A630, 630 is even. So use the first formula. So we'll have A630 divided by 2B. and that'll be A315. And since we are given what A315 is, then we just take A315, and then we add a B to the end. And for A631, 631 is odd, so we use the second formula. (631 minus 1 divided by 2), that'll be A315A. So that'll be ABB, AAA, BAAA. So any questions here? Just used it to calculate much larger terms in the sequence. Awesome. So yeah, so let's move on to a problem that'll hopefully help us kind of go over some more closed and recursive forms. Oh wait, that's later. Okay. Never mind. So for this problem, we're going to do a little bit review of logic. So remember that whenever we see the this symbol, that means or. We see this symbol, that means and then this symbol, that's our negation symbol. And then just recall that we define as well that T stands for a tautology, something that's always true. And then C stands for a contradiction, so something that's always false. So here we suppose that we're given these two logic statements. So we have A representing the statement that P or T and P or C. And then we have the statement B representing just statement P. And so we're supposed to use theorem 2 in the book to show that these two statements are equivalent. And so I've provided just a copy of all those theorems here. So we have commutative, associative, distributive, identity, negation, double negation, idempotent, de Morgan's, universal bound, absorption, and then the negations of a tautology and contradiction. So if you want to go ahead and take a few minutes and see how we can start to show that P or T and P or C will eventually be equivalent to the statement P. So go ahead and take a couple of minutes on your own, and we'll work through it together. All right, so hopefully that was enough time to kind of think through this problem a little bit. So let's go ahead and go through it together. So does anyone have an idea what might be the first step that we could take to prove this? Yeah, Ian.
So the first step I did is we combine P or T into just a tautology using universal bound.
Yeah, that's perfect. So yeah, universal bound, we know that P or T is equivalent to T. So this gives us T and P or C. And then we'd say that's by the universal bound. And then anyone have a guess for what they did for the second step? Yeah, Aiden?
I used a identity theorem to change the P or the contradiction into just P.
Yeah, that's perfect. Yeah, P or contradiction is equivalent to P. So this is T and then P or C, that's just C. And that's identity.
Would it be a T and P? Or
Oh, yes. Wrote that down incorrect. Yeah, thanks for catching me. Yeah, so T and P. And then what would be the third step? Yeah, Jim?
Oh, just after this path is done, I've got an alternate that I'm curious about.
Okay, sure. So what would the next step be here? To finish.
That'd be
to show
identity
that,
again.
well, we can't actually do identity directly here, right? So if we look at what identity says, and it's good. This is really good to
Are you
catch right
talking
here.
about commutative?
Yeah, we need to use commutative first, and then we can use identity, because identity tells us that P and a tautology is equivalent to P. But what we have is a tautology and P. So these are different. So we need to use commutative first before we can use the identity. But yeah, this is really good to catch and kind of go over here. This is a really common issue that we see a lot. So here, yeah, we need to use commutative. So this will be P and T from commutative. And then that's equivalent to P using identity. And then, yeah, so somebody asks in chat, so the order of the conjuncts matter? Yes, the order of all of these matters. And if we want to change the order of an and or an or, we need to use commutative before in order to do that. And yeah, somebody asked, I assume this is being done, just make sure we really understand. Yes, we want you to really understand how all of these statements in this theorem work. So we have to be really strict with how we treat each of these statements, just to not skip steps. And then, yeah, Jim, so you said you were curious about an alternate path. What was that?
Yeah, just recognizing the way that these are drawn up, it looks like you could use the distributive property first to get P or quantity T and C and quantity.
Yeah, that's perfect. Yeah. So we could definitely start there. So what Jim noticed is that, well, if we look at the statement that we were given, P or T and P or C, that looks a lot like this P or Q and P or V. So alternatively, yeah, we could start out and say that that was equivalent to P or T and C by distributive. And then we could just apply, so here then you could apply universal bound, T and C. Anything and C is just equivalent to C. And then anything or C is just P or C is equivalent to P, so that would be equivalent to P using the identity. So yeah, for a lot of these logic problems, there's definitely multiple ways that you can go about solving them. And this would be a perfectly valid way to solve this problem as well, starting with distributive. And then somebody asks, so do we have to get the correct order? Yeah, so yeah, when we're applying commutative, we need to make sure that, and we're applying these rules, we need to make sure that they're all in the same order. And yeah, and yes, you will be required to do that for like homeworks and exams, etc., to make sure that you like understand these concepts, and that you understand that we need to use that the only reason we can swap P and T is by using commutative, and that's why all of these work. So are there any other questions on this problem?
I just had a question in general. It seems like a lot of these logic problems are tabular that we're learning about, but I've also found learning them in terms of visually to be useful. And if you can construct a Venn diagram, does that come into play at all?
Yeah, so we will see a lot of Venn diagrams when we get to sets, which is really closely related to logic, and we'll actually see that everything we can do with sets can be done using these logic statements here, and so we'll use a lot of Venn diagrams for that to kind of visually describe that. So you certainly could use Venn diagrams to describe these logic statements, but we won't be doing that. We won't be using Venn diagrams until we get to sets.
All right, thanks.
Yeah, and then Stephen, you had a question?
Thank you. Oh yeah, just a quick question. So in relation to, I guess on a similar topic of sets, I was going through homework 1, and it seemed like, I think beyond problem 6, I think, or at least problem 6 started to include sets. So I was just curious. I know sets are later in the chapter 1 textbook. I was wondering, do you know, like, are we typically supposed to wait until we see those topics in lectures, or are we typically supposed to like read first and then do the homework, and then have the lectures, or is there like a particular? Do you know? I'm just curious.
I don't think we have at least formal sets in this homework. We'll get to like a lot of we'll get to like formal set proofs. We might have introduced the idea of like having like sets of numbers. Like a set of numbers or something. But we won't formally introduce the notion of sets and do those problems until later. But I recommend, make sure you're reading textbook, going through lecture and stuff. And I would just start the homework always early, like as soon as it's released, and start going through the problems that you've over the material that you've like seen in lecture, and that you're also like seeing while you're going through the book. Would be like a good way to attack the homework.
Okay, thank you.
Yeah. Any other questions? Awesome. So now let's go ahead, and this next problem will bring us back to sequences. And so for this one, we're going to look at the following sequence, determine what the next number is, and then we're going to give closed form formulas as well as recursive form formulas for this problem. So here we've got the sequence 3, 6, 9, 12, 15. So take a few minutes on your own to figure out what the next number would be, what a closed form, and then what a recursive form would be for the sequence. Okay, so hopefully this problem isn't too bad. So let's go ahead and go through it. So does anyone want to say what's the next number in the sequence? Yeah, someone in chat says 18, yeah. So we can see we're going up by 3 each time. 3, 6, 9, 12, 15, 18. We're just adding 3. Does somebody want to give what they got for a closed form formula for this? Yeah, so in chat, yeah, so we have for a closed form, that a sub n is equal to 3n. And we can just kind of observe that just by guessing and checking. And then what about a recursive formula? Yeah, perfect. So for recursive formula, remember whenever we give a recursive formula, we have to give that starting value. So we have to say that a sub 1 is equal to 3. And then in general, we can say that a sub n is equal to a sub n minus 1 plus 3. And we can just kind of observe this just from guessing and checking, that the next number is just 3 plus the previous. But I want to also go through a more systematic way that we can find a recursive formula if we know what the closed formula is. So let's say we were able to figure out the closed formula, a sub n is equal to 3n, but we weren't sure about the recursive formula. How could we go about finding a recursive formula? So if we know that a sub n is equal to 3n, what the trick is that we can plug in for n minus 1. If we know the nth term, we can find the n minus 1th term just by plugging into this formula. So that means that a sub n minus 1 is just 3 times n minus 1. So a sub n minus 1 is equal to 3 times n minus 3. So, and we know something about 3n, right? We know by the closed formula that 3n is equal to a sub n. So we can make a substitution here. And then solve for a sub n. So then this would give us that a sub n is equal to a sub n minus 1 plus 3. And you'll see that that's exactly what we got, just guessing and checking for the recursive formula. So for like this problem, it was pretty easy to come up with the recursive formula, but for sometimes it may not be. So if you want like a more systematic way to find recursive formulas in general, you can start with the closed formula, and then you can derive what the recursive formula is. So are there any questions over this question? I guess the one thing I will say in addition, so while it's easy to go from a closed formula to the recursive formula, in general, it is very difficult to go the other way. If you're given a recursive formula, it is very difficult to find a closed formula. So there's not just an easy way for us to do that. But for the sequences that we'll be working with and formulas in this class, they shouldn't be too bad to find what closed formulas will be. So with that, let's move on to this next problem. So we have another problem on logic. And so here we suppose that we meet 3 people, A, B, C on an island. And then we're letting P represent the statement that A is truthful, Q represent the statement that B is truthful, and R represent the statement that C is truthful. And then we're going to convert all of these statements into symbolic logic notation. So just to give you an idea of kind of how this works, we'll go through the first one together, and then I'll put you in breakout rooms, and then you can discuss with some other students on how you could convert B, C, and D into symbolic logic. So let's just go through the first one together to get an idea of kind of how some of these go. So first we have that A is lying and B or C is truthful. So how could we represent A is lying using either P, Q, or R?
Negate P.
Yeah, so we could negate P, and that would basically mean that A is lying. It's the opposite of the statement that A is truthful. And then if we want to say that B or C is truthful, then we could just say Q or R. Since that would just be that Q is truthful, or that B is truthful, or C is truthful, so that's the same as B or C is truthful. So for A, we could have the statement not P or not P and, excuse me, Q or R. So A is lying and B or C is truthful. So let me, because as soon as you go into a breakout room, you're not going to be able to see the screen anymore. So let me share the question in the chat. And then you can download it so that way you'll still be able to see it when you go into the breakout room. So just give me 1 sec. Okay, so hopefully you just got an image of this problem. So go ahead and save that if you need to look at the problem still. And then I'll put you all into the breakout sessions. So it'll be like about 4 people to a room. And then just discuss the problems together as a group. And then we'll come back in a few minutes to talk about them together. And then if you want to, Peter, you can join one as well and talk with some students, or you don't have to, whatever you want.
Sure.
And then Jace, Tanner, and Zachary, if you want to go ahead and join the breakout rooms you're assigned to, that'd be great.
I don't think I was assigned to a breakout room. It doesn't show that I'm. Because I just joined 1 minute ago.
Oh,
it just
I see.
said, right? The discussion.
Yeah. Let me put you in a room. There you go. And then Zachary, can you join yours? Okay, awesome. Looks like we're all back. So does somebody want to go through what their group got for B? That A and B are lying, or A and C are truthful? Yeah, Aiden?
We just did the not symbol, and then in parentheses P and Q, and then end parenthesis, and then we did or, and then parenthesis again, P and R.
Okay. So what you're saying, so here you're saying that it's not true that A is truthful and B is truthful, or A is truthful and C is truthful. So one thing here is to know is, let's look at a little bit more closely what's going on with this part of the statement here. So this is saying it's not true that both A is truthful and B is truthful. But what the statement we're asked is that A and B are both lying. So this isn't actually quite correct. It's very close. But what we want instead, and I'll kind of explain why, is we want not P and not Q, or P and R. Yeah, Stefan, you got a question?
I just want to defense and aid in this was partially my solution. We were in the same breakout group. It works if you add a second set of parentheses on the left. So you start a new parenthesis, and then before the or, you add another parenthesis, a closing parenthesis.
Like this?
Yes, because then distributive will take care of it. So it's still in parentheses.
Not quite, because remember, when we use De Morgan to distribute the not, the and flips to an or.
Yeah, so you can negate the entire, you can negate a disjunction, but you can't negate the conjunction to, yeah.
Yeah,
Or
because
'cause-
not P and Q is not P or not Q.
Yeah.
But you know, this is very close, and it's a little bit tricky with these like statements in English to try to like convert them to logic, because unfortunately in English we're extremely like imprecise with our verbiage and the way that we talk. But I just want to kind of explain this a little bit, because what this statement is saying is that A is lying and B is lying. So we know that they're both lying. But this statement is saying that it's not true that that A is truthful and B is truthful. So in the first part, we could have A lying and B telling the truth, B lying and or B lying and A telling the truth. But we want both A and B to be lying, so we need to use this one instead, because this tells us that A is lying, that both of them are lying, rather than just at least one of them lying. Now, we also could use De Morgan's law here, and what would also be equivalent is we could say that it's not true that P or Q or P and R. And that would be equivalent. So this would be saying it's not true that A is truthful or B is truthful. And that would be an equivalent way of converting that statement into logic. Are there any questions about this? Because it's a little bit subtle why the two of these are different, but I hope that makes sense. So any questions on this one?
So if it was P or Q, then you could just keep the not outside like that. That applies to that. You can't do that when it's the and symbol.
Yeah, because what we have
De
is
Morgan's.
yeah, De Morgan's. If we do De Morgan's over an and, then it switches to an or, and then if we do not P or Q, that'll be not P and not Q. So whenever you use De Morgan, it flips the or to an and to an or.
Okay, thank you.
Yeah, no problem. Any other questions? Okay, awesome. We'll just hurry through the last few. So for C, I'll just go through one possible answer. So for C, we could do P and Q, or P and R, or Q and R. So basically just saying that if at least two people are telling the truth, then either A and B are, or A and C are, or B and C are. That's kind of the way that this statement works. And then for D, exactly two people telling the truth. One way to do that is basically to say that either A, B are telling the truth and C is lying, or A and C are telling the truth and B is lying, or B and C are telling the truth and A is lying. And there's a couple different ways you can represent C or D. But are there any questions on these two for C and D? Awesome. So if there's no questions, it's basically we're right at 12:40, so right at the end. So thank you all for joining the discussion today. I'll be having office hours later today from 2 to 4 p.m. So if you want any help on any of the homeworks or any of the material that we've gone over through this past week, please stop by. But other than that, thank you all so much for joining today.
Thank you.
Yeah, thank you.
Can I ask you a quick question now about the quiz?